Alright, continuing on with my motor drive design. This is the schematic of my motor controller, which I've been working on in many videos that you can see on my YouTube channel. And I'm done now with the review of this schematic. So I've reviewed every single component, and I also reviewed every single label. So hopefully there aren't any other issues that I may have missed. But you can never be sure. So maybe there is something left in here which I will discover as I start laying out this board. But I feel that this schematic is now ready for a layout. So I'm going to start with a layout in this video, and I'm going to start by doing the component placement. So I'm going to go through every component, and I'm going to place all of the components on the PCB. And then once all of the components are placed, then I'm going to start with the actual routing. So let's get started. I've updated all the fields, and I've annotated the schematic. And let's see how this goes. And I'm going to do update of this, let's see, update PCB from schematic. Update PCB. Excellent. Close. And we got a few more components which haven't been there before. But the first thing I'm going to do is just make sure that my windows are side by side, because I work with KiCad when I can click on one side, and I can get the component selected on the PCB side. So let's make sure that the schematic is here as well. Let's see. We have to do. And let's see. There we go. And I can make both windows, let's see. I can make them both always on top right now. Or at least one of them. Anyway, I'll make them both always on top. And I'll just, let's see here. I'll just move it here. I wish there was a way to make the windows transparent. That would have been really cool. At least not in this version of Ubuntu. So where to get started? I want to get started with sort of the parts of the schematic that are most critical here, and I did the motor drive with the driver layout, so I'm just gonna continue with that, and I'll continue placing the components that are part of this motor driver circuit. Let's see. So as you can see here, we have one of the transistors is placed in the wrong place. So I'm going to move it here. And also I want to change this this grid. So instead of 0.25, let's see, instead of 0.1 millimeters, I'm going to make it more like maybe 0.5 millimeters. Let's see if this is better. Make sure that all of them are aligned like that. Alright. So now we have a bit better placement of the transistors, and this would be the motor connector. So the motor connector will go directly to the transistors. It's going to be very close to the transistors. which is perfect, right? Because the traces that are going to be going from here to the motor connector are going to be very thick, and basically we can just go directly to these connections here. So if I select one of the components, the component gets selected here as well. And now it's a lot easier to see because I have this, I've created this circle around the cursor, so I can much better see which component is selected. And now it's kind of like weird there because it shows the capacitor and not the transistor. Let's see if I do like this. Yes. Okay, so it seems that the cursor is actually not being updated in KiCad once I zoom in or out, which seems to be a bug, but it doesn't matter for now. Let's see. So let's see what we have here. We have I'm going to move all of these resistors here, and I'm going to, let's see, I'm going to move the DRV chip a bit closer here so that I can see how the connections line up. So ideally what I want to do is make sure that the connections are as straight as possible. So anything that goes from the DRV chip to the MOSFET should be able to be placed on the same layer. So kind of like anything that signals the MOSFETs it would be best if it was directly connected on the top layer and without any bias. But we'll see if that is possible. So we have a few connections here. What is this? This is the C phase. So it's quite possible that it would be better to actually rewire this connector in order to get the phases lined up with the same layout as they are on this chip. So we can see that we have C phase is at the bottom, and then we have the B phase and the A phase. But we have on the connector bottom and then B phase and C phase. So this is not optimal. It would be better if these phases were actually reversed. So I can edit this part. Let's see. Okay, I'm going to turn off this always on top. And I'm going to open up the component editor. Let's see. This is quite easy because I have all of the components in my own library. So whenever I see such little minor issues, I can easily correct them. So I'm going to make this one pin number 1, and I'm going to make this one pin number 3. And I could either do this by modifying the footprint or by modifying the component. But I think it's more correct to modify it in this pinout rather than on the footprint, because if I modify it on the footprint, then it's going to be only on the PCB that it will be different. But when looking at the schematic, it would appear as though the pins are connected in a different way. So it's better to modify it here. So let's see. I'm going to save this, and I'm going to update PCB from schematic. All right. The connections of these two MOSFETs. So this one and this one. Let's see. And this one. Let's see if we can get better alignment now. So there's still certain things, like for example, what is this? This is pin number 3. So that is SLA. What is, okay, so pin number 3 is actually this current sensing input. So it seems like let's see, and where does the gate connect? So if I select that one, come on, I don't want, yeah, no, I have to cancel the tool. So if I select, can I select that one? Yeah, so that is R102. Let's see where we can move R102. All right. So that connects there, and then we have number 4 here, which connects then to a few resistors here. So we can move these resistors and make sure that they're in place. They will be here. So R140 is the pull down resistor, which can be there. What is this? This is the voltage sensing. Alright, so I can move voltage sensing here. And I can move this resistor here. Okay. Can we get it aligned? Okay. I can actually align them later. I can do like this, for example. Let's see. Align to the left, to the right. Let's do it to the right. Okay. And where does this connect? Okay, that's ground. So we can rotate this one. That's better. And then this connects to the B signal. And finally we have this, which connects to the C signal. Maybe I should use a slightly smaller grid. Okay. So just looking, I can actually go like this. I can start with the top one, and then I can look at every single signal that comes after it. So these two will ultimately route in this direction and directly connect. So that's fine. But then we have this one. It's connected to a capacitor. So we can move this capacitor in place as well. And it's essentially just a capacitor that will be routed like this. And then high B, high side on phase B, needs to be connected like this. Let's see here. So maybe it's better to actually have the capacitor like this. If I have the capacitor like that, I can then route this directly underneath the capacitor. Not the best place to route this, but at the same time it keeps everything on one layer. And by the way, this is going to be a 4-layer board. Let's see if we can change the layer. Tools, set, let's see. Layer setup. This is going to be a 4-layer board. Signal, signal, signal. Yeah. Okay. I'm going to turn off the fab layers. Next, let's see here. So next would be this pin connects the capacitor, and then there is this one. So actually it's better to move this capacitor a little bit. Maybe like this. And then this one routes directly around here. Or actually, let's see. Yeah, that one goes just there. And then we have this one that goes there and there. So ultimately, this needs to be actually moved slightly. I could move it there, but it would be better to have something that. Let's see. It would be better to move actually these two upwards, because we have a lot of space there, so we can move this one here. And then we have a trace that goes like this and directly there. So that's good. And then the designators. I'm going to move them like that. And there is also, let's see, there is also some resistors here. So it's that resistor, and I think there should be another resistor. It's probably that one. So these ones are going to connect to here. Let's see. And I can also move this slightly upwards and keep everything aligned. Like for some reason I cannot actually align them perfectly, or can I? Maybe it was because I selected both of them like that. Okay. It would be nice if KiCad supported kind of patterning in terms of where you can just lay out one section and then select a bunch of components and lay them out in the same way. That would be helpful in this case. But as far as I know, KiCad does not support that kind of functionality. Okay, so this resistor is there. And where is this resistor? It's right there. Let's see. Where is this resistor? Okay, what the hell just happened here? Okay. Alright. And then there should be, I think there should be some components connected here. Yeah, we have this resistor, and we also have this one. Let's see, R100. And then there is also the diode, I think. So where does this diode go? Let's see. This diode should go, I think it should go here somewhere. I'm going to try to select just one net. There we go. So this diode should go here. It should be placed somewhere in between there. So actually, okay, I'm going to leave it outside for now. And I'm going to try to place all of the resistors first. So we got that one, and we can also move these two resistors here. I'm going to move them here. No? Yeah, that's better. Okay. I'm going to have to move this section a little bit upwards later. But first I'm going to place the components. Okay, so R150 is a current sense resistor, and that's connected to phase B. So it's connected to this, let's see, that's ground, okay. What about this one? So this essentially needs to go somewhere here. And that means we have to move this chip out a little bit. Let's see. We got R150, and the second one is called R114. Let's see. And this also connects to a capacitor, which I'm going to place close to this pin, because that's where I want to filter things. So I'm going to place this one like this. And depending on what this is, there is ground, and then there is this pin. Which pin is that? That's the second sensing pin, okay. So let's see. In that case, it's better to place them like this. So they will connect, they'll go directly there actually. And then they'll connect through a via to the ground on the other side. Alright, and then next I want to find the second capacitor. Let's see, this should be somewhere here. Where is this second capacitor? So the second capacitor is this one. Oh, it's buried there. I'm gonna bring it up. One thing that would be very useful is if KiCad supported some kind of functionality. When I mouse over a window, I want the window to be selected. Actually, that's probably the window manager functionality, and I'm not quite sure how to configure that. But it would be very nice that if I move the mouse from this window to this window, that this window will automatically get focus, so I don't have to click on the second window. Because every time I click, I sometimes click somewhere where it has some side effect. So it would be very useful if it was possible to just mouse over a window. Let's see, I'm going to place this one there. Next, let's see. Where can we move from here? Could actually just check that we have all of the components here. So R100 needs to be a little bit closer there. Probably also like this. Yeah, that's better. And I have to move them one by one, because if I move them two together, then I don't get the same alignment to the grid. Okay. So this one goes to that pin. So naturally here we're going to have a very thick trace, which means that we want to essentially move these two farther down. Let's see. So it would be better actually to move them down. Actually, what would be optimal is to have this resistor directly at the edge of this pin. That would be the best solution, because this is going to be a high current path. So this goes from the VMOT. This is going to be the ground path for the motor. So this is going to be a very high current path, and any trace here is going to get hot. So therefore it's better to move this out a little bit. Let's see. Maybe if I press M when I'm hovering over this transistor, maybe I get the center point of that transistor. Apparently I don't. So let's just make sure that everything is aligned. So then I can free up a little bit of space here by moving this so that it's aligned like that. And then I can move this one also so that it's aligned to the second one there. And now I should be able to place this resistor a bit closer, kind of like that. Let's see. Okay, that's much better. This is the gate, as you can see there. Much easier to see with a circle. I really like that change that I made to KiCad. Alright, so this will connect directly to this pad on this resistor. And let's see, so if I just deselect everything, yeah, okay. And I'm kind of thinking that maybe it's better to move it out just a little bit, and to have like a copper area here, which I connect also to the other side of the PCB, and kind of get a better heat sinking capability of this junction here. Let's see. What would be the best place to put this? Like this, maybe? Alright. Got R14 there. And just gonna move this references a little bit. Let's see. Okay, this should be fine. So I can have a few vias here that go directly to the other side. Area on the other side for this resistor. And the next would be this resistor. So I really have to move this transistor out a little bit. I'm going to move both of them. Let's see. So this belongs to the other one. Something like that, and I can move this one also slightly out. Okay, I have to select all of them, and then I have to move the ones that belong to the other transistor. These two. Let's see. Come on. No? Let's see. There we go. So, no? Seriously? God damn it. Yeah. I don't understand what the purpose is of that. So if you select some pad, you can actually move that pad. And what is the purpose of that? Like, if I need to move the pads, then I should be doing that through the component library. So I should be actually updating the footprint in the footprint library and then assigning that footprint to the component. So the footprints should not be modifiable on the PCB. Let's see. And then I can just move the whole block here and make it aligned like that. Maybe a little bit down. Let me just move this resistor in place first. So the resistor will go kind of like this. Yep. Come on. There we go. All right. Let's see, just to make it uniform, I'm gonna just select this one and move it just a little bit. So just here. And then I can just select this, this, and this, and distribute uniformly. So KiCad is perhaps not the most advanced layout editor, but nonetheless, if I use the functionality that is provided, make the best of it, it's pretty much always possible to achieve anything that I can think of on the PCB. It can just take a little bit more time, and if it's not possible in the UI, then it's usually possible through the Python scripts. And that's really powerful concept. So for example, it's very easy to create footprints from Python. If some kind of advanced footprint is required, it's easy to create it programmatically from Python. Let's see. Come on. No? Yeah. It is really just a matter of taste if you want to have perfect alignment or not. I like to have things in alignment because then the tracks end up being straight or almost straight. Let's see. P45 is the motor connector. We can place this text there. Or actually, I'm going to place the text. Let's see. Yeah, I can leave the text there. See, so, and then this can go. Let's see. This can be aligned with the MOSFET there. Yep. Now, what else do we have here? We have this connection that goes all the way there. The ground we don't need to worry about because that goes directly to the ground plane. But I want to avoid any crossings. So anything that has to cross, that's not a very good thing to do. But it looks like I cannot avoid any crossings here because I have to connect this current sensing tracks to these two pins here, which unfortunately means that they have to go through a via, go down on the bottom layer, and then come back up here. But as long as that's the only thing, this is going to be fine. So I think we can move this a little bit closer now. Maybe that's a bit too close. I wonder if there's anything else that has to go here besides the diodes. So the diodes go to the voltage sensing resistors, which are here. Essentially, the diode. I think that what I'll do actually is place this diode and this capacitor closer to the CPU. The capacitor will have to go there anyway, so might as well place the diode there as well. So, okay, what is this? This is capacitor that goes there. Okay. This is the PVDD bypass capacitor. And let's see what we have here. So these two are also going to be placed at this place here. Right. And then we have this capacitor. Okay, so these capacitors are the, let's see, this is booster capacitors that have to go here. So they can basically be placed here. So this pin will go underneath the there. So it will have to go like this. Yeah, and we can definitely not place this pin or this track through here, because this is going to be just filled with copper. So this has to go there, and then these two will go here. So we need to leave a little bit of space there. And then we have the third capacitor, which is this one. This also has to be placed here. And this needs to have some space as well. I wonder if that would be enough. Let's see. Niklas is saying, tjenare mannen, ska kolla dina andra längre designvideos vid tid. Kul att se någon från Sverige som jobbar med KiCad. Ja, det är kul att jobba med KiCad. All right. Is there anything else here? Right, we have the two bulk capacitors there. These two need to go on either side of the... Oh, damn it. Damn it! Come on. This is so annoying. Okay. And then I have to click like that. And then I have to move this one here. So they're going to go on either side of this driver circuitry. Let's see, what is C45? Okay, so C145 is this one. This is going to go closer to the CPU. And it can actually go, it can actually be placed right by the diode as well. I can move this one just here. And this one has to go to VMOT. So the way I'm thinking that VMOT is going to be connected here is that it's going to go underneath. So I'll have, on the top layer, I'll have the SLA, SLB, and SLC. And then VMOT is going to go underneath, and it's going to come out here through many vias and like a copper pad and connect to each transistor there. So I'm going to have the bulk capacitors on each side of this motor connector. So the second one is going to go to the other side of this. Let's see. And just because I'm trying to be a perfectionist, I have to align these two. Align this to the left. There we go. And unfortunately this one is a bit too close for my taste. So I'm going to move it up a little bit. Yeah. And I haven't drawn any silk screen for the transistor, which I should have done. But I think it's pretty clear that the transistor goes sort of like it starts here, so the package goes all the way around here, but it doesn't go farther than this smaller pin there. So it kind of goes like this. And then I have the 3 capacitors that are going to be connected. Let's see, they're going to be connected by the MOSFETs essentially. So they go to VMOT, and let's see. That would be a good place to place this capacitor actually. Let's see. So SLA has to go to this capacitor, which means that I have to place this one a little bit farther. I have to have a little bit of space there. But then I have the ground. So actually what I can do is place it here. That's a bit better. Because I want to place it as far as possible to this side so that I can have a big copper area here. Great. And the second one goes, let's see, it doesn't really matter. It doesn't. This will be aligned like this. This can be placed here. And then I have to move this one out a little bit. So the purpose of the bypassing capacitors is to provide switching current. And that's true for every single bypass capacitor that you see on a circuit. They provide they provide the store for the current for when you have to switch something. So if you have a load that you're switching, the bulk capacitors provide this extra current so that the current doesn't have to come from the power supply. And that is very good because when the load changes on the power supply, that also changes the voltage on the power supply. So any change in the current will also add noise to the power supply rails. So that is what we're trying to avoid essentially by placing bulk capacitors which can provide that current instead. And so the way that the power supply rail is then connected is essentially going from here, for example, and then passing this capacitor and then going farther, instead of kind of going maybe here and then going like, or maybe let's say instead of going like this, instead of going here and then there and then there. Let's see here. There's going to be a large copper area underneath here that VMOT pins are going to be connected to. So I got all of, let's see, I got the third one here, actually. The third one needs to go to the third MOSFET. Using the capacitors like this, the ceramic capacitors, decreases the series resistance. So we get kind of the benefit of both worlds. When we have an electrolytic capacitor, it has a high series resistance. When we combine it with a ceramic capacitor, we get lower series resistance and slightly higher capacitance. Okay, that is fine. Now maybe I should actually move this one up a little bit. Only slightly. Let's see. Like this. So now I can connect the SLB to here. Let's see. Come on. Cancel. Yeah. Okay. Yeah, I have to move this to slightly upwards because I need to make room for that SLB line. And I can move the two designators slightly down here. I've tried making boards before without designators, and I've personally found that to be very annoying. Because the moment something needs to be located, it becomes hard to do that. So you have to then look at the print of the PCB, kind of try to find the right component. Designators are very helpful. And the same thing with this, I think. So I got this SLA there, and then it continues down. So I have to move these two up a little bit, so I have a little bit of room there. Okay. Looking good. We have the diode here. This goes to the resistor. And actually, what kind of resistor is this? So let's see. R190. Actually, now that I think about it, I think that placing, let's see. So I can actually place the R189 close to this, close to the transistor, but then I can place R190 closer to the MCU pin. Because then this rail will be higher current, so it will be more, or higher voltage, so it will be more resistant to any noise. And once it arrives closer to the MCU, I can then pull it down. That would be one alternative. Let's see where this one is. That one is there, and this one is here. R189. Could actually place it here. That'll be a better placement for it. I'm actually gonna move the R190 close to this resistor for now. And the C149. Let's place these capacitors here. So C123 is the other one, and the diodes as well. They can be just sitting here waiting. This diode is there. Okay. Let's see. All right. What we also need here is the Hall sensor connector. And this footprint looks wrong. This footprint definitely needs to have more space. Could it be that I've actually forgotten to change the footprint of this symbol? So I remember adjusting at least some of these footprints. Let's see, con Hal. I'm going to open up the datasheet of this connector. Because this is a horizontal connector that expects to have a connected to it, and it needs to stick out around 5 millimeters outside of the PCB. So it could be that I have correctly designed the footprint and made it a little bit smaller because it has to stick out 5 millimeters, but I want to just double check it. So 9.2, and if we just remove 5 millimeters, it's going to be 4.2. So the footprint needs to be, let's see, unselect all. The footprint will need to be 4.2. We can just do like this actually. Is this 4.2 millimeters? Yeah. So that's fine. So as long as we just place this sort of aligned with the motor connector there, it's going to stick out a little bit here, and the terminals are going to be connected to this part that sticks out. Okay. So next I'll just move the resistors here. They're going to just go in series with the lines, but then go to the MCU. Also, I think the other thing that's missing from KiCad is that I cannot select multiple components, can I? If I just select, like, okay, I don't think I can. Damn it! Damn it! I had the focus in the wrong window. I don't think, no, I can't select multiple components. So I can only select one component at a time, which makes this task much more time consuming than it should be. Okay, so next resistor. I'll move this resistor. Yeah, so this is a live stream, and that means that you can comment in the comment field, and you can ask any questions you feel like asking, and when I'm not focused on the PCB, I can read the comment field and then reply. I have the courtyard. The courtyard is this gray part here. It's quite small for some components, because this is the default footprint that is provided by KiCad. I have made an attempt to generate my own footprints, where I had a courtyard determined in a similar way that Altium does it. So I had like 3 different variants with different courtyard around them. But for this PCB, I decided that I'll use the KiCad default footprints, because I had some problems with the footprints that I've generated. When the components were soldered, sometimes the components will go on the side because the size of the footprint wasn't precisely correct. So it's better for this board to use the default footprints, but once I've fixed my own footprints, then I can use the footprints with proper courtyard. Did that answer your question, Nicholas? Or did you mean something else? Okay, I'm going to move on to the next resistor here. Let's see. Actually, I can place them side by side here. And another annoying thing is that if I press the M key when moving the component, and I don't have the cursor close to the center, it's going to align to the wrong point on the grid. So it's going to be like a center of the pad, and if I move component when the cursor is at the center of the pad, then the component is not aligned. Let's see. So this one goes to the yeah. Have to rotate this one. Come on, rotate. There we go. So this goes there, and then this also needs to be rotated. And then this goes to the MCU. Right. Okay. And I did the same mistake here. So I'm going to correct it. Let's see. There we go. And this will be the ground, so this will go just directly to the ground plane. And this one as well. R183. annoying thing with KiCad is that it doesn't yet have the functionality to allow you to place components so that they don't intersect. At least I don't know if it has that. I haven't seen that yet. That's very useful functionality that Altium has. That you can just have the components aligned by the courtyard, but in KiCad you have to actually place them on the grid. Okay, and then the last thing is this one. And what would be a good place to drop this one? Let's see. Yeah, pretty much like that. Something like that. I can move this a little bit out. And then this one will go in between there. Yeah. I wonder if I place it here, and then I can just probably select it like this. Move it together with that. Let's see. So now select that first. Let's see. Okay. So this goes there, which is the ground. This goes there. This goes there, and then straight through it, and it's going to move underneath the component there. And then we have this one goes there. Yeah, that's good placement. I have to keep the cursor precisely at the center there in order to move the components and keep them on the grid. Yep. Next is this capacitor. This can go right here. And the temperature sensing resistor. What would be a good place to place the temperature sensing resistor? I want to place it in the middle somewhere. So there will be, VMOT is going to be a large copper area that goes here and then goes to an inner layer. And then there will be a ground plane that goes that connects these to the ground on the inner layer as well. So where is the heat gonna go? I want to place this resistor somewhere where most of the heat is going to be. I'm going to leave it on the side for now. Yes, you finally did. I told you I were gonna live stream yesterday, but you never showed up. Alright, so I can move in maybe some capacitors here. Let's see, that one can go there. Maybe like that. Yep. And the analog supply bypass capacitor. There is a very good application note on minimizing electromagnetic interference from TI, which explains very well the function of the bypass capacitors. So the bypass capacitors are there to provide extra current. Whenever the circuit is switching, they provide extra current so that the current doesn't have to come from the power supply, which minimizes the noise on the power rails. Yeah, you had a walk, that's fine. You're here now. Alright, so next, I think I'm gonna check if this capacitor is in place. Yeah, that one is there. The two resistors. The two resistors here are diodes that clamp this this signal. Let's see. What will be the best place for them? Did you have a question or something? Did you want to ask anything? You can ask it right now. Let's see. So this one is probably gonna be rotated, yeah. Let's put it here. And then this one goes to that pin. Okay, great. And I can have these two in between them. Actually, I can have them there. If I move this one out of the way. I have to check if there is a way to change the size of all of the designators, because I would prefer to have them a little bit smaller. Oh, damn it. Oh well. Had to rotate the resistors. Okay. Yeah, that's fine. And this diode. So what's gonna happen, because the voltage swing on the so this chip has a built-in current amplifier. It is connected through these pins, the current sensing output 1 and 2, and these go to the MCU. Now, the datasheet specifies these pins as being from 0.3 volts to 5.7 volts, which is way too much for the inputs, the analog inputs on the STM32. So what I do here is that I pass them through the resistors, and then I clamp them with this diode, so that they're always clamped to 3.3 volts. And by adjusting the gain later, I can make sure that the current sensing is within the 3.3 volt range. So this needs to be rewired, because the way that the footprint of this diode doesn't really fit together with the layout of this circuit. So what I have to do is just reconnect these pins so that I get I have to swap pin 3 and 1 and pin 4 and 6. And then I'll have them in nice straight lines, just going straight from the resistors to the diode and then farther out. So I'm going to place the B sensing on this pin, and the A, let's see, I can make, actually, just delete that line as well. So this will go here. This will go straight down here. And I can just move this. When I press the G key, I can move the wire. Okay, let's move that wire actually as well. Just a little bit. And I'm going to do the same thing to the other one, to this one. Just so I don't forget to update the schematic there as well. Okay, and this one goes here, and this one goes here, and then this one goes like this. All right. So I'm going to save that, and then I'm going to go, damn it, and I'm going to go to the PCB editor and update PCB from schematic. Close. And now the pins are connected in such a way that makes routing much easier. All right. Let's see where I have all of these. I'm gonna, yeah, like that. These are the test points, so they're just little pads, and they have the wrong footprint. Let's see. I think I'll place them there. So this would be pin 22. So then we have all of the other control signals just coming right after that pin. They can be here. But I think that they're a bit too large. Like it's not really a problem to use to even test directly on this IC. So the size of the test point, that's about the width of this pin, that would work. But of course I want to have the test point a little bit larger, but not this big. This is just too big. So I'm gonna change this. First of all, I'm gonna check which footprint this is using. I think it's a custom test point footprint. Test point pad 1 times 1 millimeter. I'm gonna create one that is, let's see, maybe half that size. Let's see. Was that in the test points library? Right. Okay. Let's see. Maybe there is already a footprint that is suitable. It's worth checking. Test point. Let's see. 0.8. Seems to be that. Let's see. That's 1 times 1 as well. So 1 times 1 is the smallest test point that KiCad has. Test pad 1 millimeter times 1 millimeter. Okay. Fair enough. I can just adjust the size and save it as a custom. So this can be 0.5. And this has a mask, but it doesn't have any solder paste, which is correct for a test point. So this is going to be bare copper. And test points don't need a silk screen. And they don't, yes, they do actually need a reference. So we can keep the reference. But we don't need a silk screen. And we don't need any, or actually I can keep the courtyard. I can just make it much smaller. Let's see. So I want to have 0.2 millimeters between these pads. So that means I can place the courtyard at 0.1. Yeah. That would guarantee that there is enough space around it. So I have a courtyard that is 0.15 millimeters, which I can then use for alignment. Yeah. All right. Yeah. And I'm going to save it in my custom library. And pad to use the new footprint. So I have all of my components in a project library. So I can easily just change the footprint of one of them and then update the schematic. Let's see. I think I saved it as 1 times 1 millimeters. I guess I did. So I'm gonna just move it. I'm gonna move it through the terminal. Let's see. I'll check the chat in a bit. First I'm gonna move this footprint. So move test point 1 times 1 to test point 0.5 times 0.5. Alright, so now I can set the new footprint for this test point. Okay, save the library and then update all the fields. Update field values. And then I have to save the schematic and go to Tools and update PCB from schematic. I wonder if I still have to update the footprint separately. Okay, apparently I didn't have to do that. So close, and let's go to the next one. And it's much smaller, much nicer. This is definitely much nicer. What part of Sweden am I from? I'm from Stockholm. I live and work in Stockholm. All right. Next test point. And the next test point. Looks like that when all the lines are straight. Okay. So all of these tracks need to have enough space here. So I think it's probably a good idea to move this block a little bit down. And then to move this capacitor further up. Okay, yeah, that makes total sense. This can even be there. And then we have the overcurrent mode, which goes directly to a GPIO pin, and then we have the gain here as well. I think there's enough space there to sort of route them. Let's see, yeah. I have to set the track size. I'm not going to do any routing right now. I'm going to place the components first. Can move this one here. looking good. And there are two more test points there for the gain and the DC calibration. So the gain pin chooses the gain of the current sense amplifier, and it can be either 20 or 40. So you basically amplify the voltage across the current sense resistor, and what you get on the output is either like, I think it's 20, maybe it was 10. Anyway, there are two gains to choose from on this chip. And the DC cal is for measuring the offset. So because this is a bidirectional, be floating somewhere between minimum and maximum when the motor is not running. So you need to know the midpoint. And for that, you can use this DC calibration input to put this current sensor into kind of DC offset measurement mode, which just outputs the DC offset on the current outputs. I think what it does is it disconnects the stage. So essentially you get the 0 point. And then you can measure that 0 point, save it in the software, and use it to determine the exact current. Okay. And it would also be a good idea to place these op amps close to the power stage. Let's see. So that the analog signal that then goes to the MCU is a 3.3 volt signal instead of something much smaller than that. Although it's not going to be that much of a difference here, because this has a 1.5 gain. Let's see. So this resistor can go there, and then this goes to the raw input there. Okay. So I think this will require switching layers for this signal path. I think that what I'll do is just I'll assemble this circuit on the side here, and then I'll move it to the best place a bit later. So this would go, let's see, this will go close to that resistor. What is this? Okay, this is going to have another resistor divider. This is the gain of this op amp. And then this goes here. I'm going to just route this around and connect it to this pin. This goes there, this goes to the sensing input, this goes to the first stage actually, so this is actually better to be placed here. Let's see. I'm going to move all of this stuff closer here. I'm going to assemble it here and then move it in place. Much easier that way. Okay. This goes to pin 7. I have to rotate it, this. And this one as well. Can I move this with, let's see, if I press M and then just, yeah, I can move it with the arrow keys. R94. Has to be rotated. And R, let's see, R96 is there, R95. And the first stage here is acting like a voltage offset. Damn it. Okay. And then this bypass capacitor, this one will go somewhere close. Let's see. So we have, let's see, that's the main power pin. So I need to move these two resistors. I'm going to move them when the cursor is aligned with one of them. I think I have to select both of them like that. And then I can just move this capacitor here. So this has to be as close as possible to the power pin, because this capacitor will provide any extra current that the op-amp needs. Again, let's see. There we go. I'm going to move this one. One good thing about this standard packaging of the op-amps is that the feedback and the output are close together, so you just connect them with the shortest path possible. Let's see. So this one goes there, this one goes... yeah, these two are connected like this. Cool. And then we have R193 there as well. Okay, so let's see here. This one will have to go around. Let's see. So it's better if I just move them a little bit so that I can... can I actually do that? No? It would be better to swap places because then I can just connect them like this. So if I swap the places and then I place this one, let's see, yeah, and then I place this one here. So these two connect together. Let me just deselect this one. So these two connect like this, and this one connects straight through like this behind this resistor. And ground goes directly to the ground plane. So this is much better. Maybe I'll just edit this PCB new file in Vim and just replace the size of all of the designators with something a little bit smaller. But I have to check the minimum size first. The minimum solder mask text size. Okay. I'm going to move this somewhere closer to this circuit, and let's see how this connects. So it's pretty much unavoidable that I need to have tracks that go on some inner layer or on the back layer, and then come out through vias and connect to this op-amp. So I'm going to leave it here for now because I want to route this part first and then see a way to connect the signals that go to this op-amp. Right, so in order not to keep this video way too boring, I'm not going to repeat the same thing right now with this op-amp. Instead, I can take some other part of the circuit. Let's do the EtherCAT. Come on. Can assemble it there. And we have two RG45, which will go there. Let's see. That's an interesting way to. Let's see. So this is a lot of tracks that cross, which is not very good. So ideally this should go the positive, because this would be differential pairs. Let's see, we have the RX pair there. So this shouldn't cross ideally. Let's see. That one goes there and this one goes there. That's really weird. Is my connector wrong pinout or something? Or some non-standard pinout? Because it's the same thing with that one. The proper way to connect this would be that you have the positive and the negative right close to each other. Okay, that's the TX, and that is okay, right. So maybe they are. So that's the RX, and all right, yeah. So they were close together. It's just that I selected the TX instead of the RX. So we have the RX positive negative and TX positive negative, and they go close to each other. But they cross. But that's not a big issue. I can just have them go around in some smart way, so that they are close together for as long as possible, and then they split. So it would be best if these lines were if these lines did not cross. But I guess I'll have to deal with this crossing. Okay. So the Ethernet capacitors. These are that their function is to smooth out the slope. So let's see, there are 10 picofarads. Placing a capacitor between like 10 picofarads to maybe 1000 picofarads usually So the reason for usually placing that to ground is to smooth out the slope of the signal, because the radiated electromagnetic interference from a trace is proportional to the slope of the signal. The faster the slope of the signal, the more the trace will radiate. So it's usually beneficial to smooth out the slope of the signal, so that it's not just goes straight up, but rather becomes a smoother slope. So that's why they place capacitors here from each of the lines to ground. Okay, so what would be the best way to place this? I think I'll just place them like this. So I'll sort of just route through this and then continue. Let's see, or I place them on either side actually. So I have my TX line there, and I have another TX line there. So I can place the capacitors on either side of these lines, so that I just route the differential pair in between the capacitors. The second one there. Place them aligned with the sides of the pins, so then my differential pair will go between these two capacitors, and they'll just connect to ground just through a wire. Let's see how long it's going to take before my dog wakes up. She's about to wake up. She's been sleeping for a while, and that's what she sounds like when she's groggy and she wakes up and she's like, "Oh, I'm so groggy," and like she's not even hungry. She's just rolling on the floor and making funny sounds. Okay. I guess I'll just place the other two capacitors, and then Alice, lugnt. And then I'll take a break. So these two need to go as close as possible there. Let's see. We have the second one here. So around 4 units in between, but I have to place the cursor in the middle of the capacitor to get it aligned with the grid. And I press M and I just move it just a little tiny bit. Let's see. And then I have enough room to route the differential lines in between there. But I'll just move them, these capacitors, a little bit to the side. Let's see. So just so that they're kind of aligned with the pins here. So one pair will go here, the other pair will go there. And I'll continue with this in the next video. So thanks for watching, and goodbye for now.